Hi. Today I will be talking about my recent work, which I have done in collaboration with my collaborator Saptasya Ghosh, Poloni Nandi, who is a postdoc at USA, and my supervisor, Professor Arvind Bhattacharya. The poster is about the finding supergravity partition function from Super-Teichmuller TQFTs. So in the introduction section, we compute the partition function of n equal to 1 supergravity for different boundary topologies, such as punctured sphere topologies or torus topologies using the Super-Virasoro TQFT techniques in ATS3. So we used fusion and modular kernels of the super Liouville theory to compute the different channel blocks, such as necklace channel blocks and the OP channel blocks and other cases. And we showcase the formalism by proving that the inner product holds for superconformal blocks, which are defined as the states in the Hilbert space. And finally, compute the out-of-time order correlator for the torus topology with superconformal primary matter insertions and investigate the early time behavior. Then in this section, I discuss some known facts from the Virasoro TQFT. So Virasoro TQFT is a Teichmuller TQFT. The Hilbert space of this Virasoro TQFT are the endpoint conformal blocks. So when you choose a initial value surface sigma and you choose some flat PSL2R cross PSL2R bundles, the reason of two copies of PSL2R is the phase space of the gravity is two Teichmuller spaces. So this PSL2R cross PSL2R phase space is associated with some fibers, and the sections on these fibers. So the states are basically denoted as the sections, and these are the conformal blocks. And for Liouville cases, these are Liouville conformal blocks. And for supergravity, these are super conformal blocks. Now, the next thing to define is the inner product of these states, which are defined here. And the inner product of the super conformal blocks is given by this integration over the super Weil-Petersen volume and the other conformal blocks with the time-like super Liouville partition function. And remember that we are integrating here over the total Teichmuller space instead of the moduli space. So then the gluing techniques I have defined by defining the module volume of the moduli space. And then I define the n equal to 1 supervisor. There are spin structures, different spin structures, because we are doing with super things, and because there are different spin structure like even and odd. Then I have defined different TQFT techniques like braiding, fusion, modular S transformation, and so on. As the TQFT phase space doesn't match with the graphite phase space, we have to define by the map function, which is basically the mapping class group. Then I computed the partition function for spin instruction, partition function for different, describe the how to compute the partition function for sphere topologies, the torus topologies, and so on for torus wormholes. And then I describe how to compute the partition function for large number of boundary cases, such as four boundary cases and so on. And then I show the results for how to compute the OTOC for uh, for our structure, and we find this graph which shows exponential behavior, though it's a non-normalized OTOC, and this gives a proper description of chaos, let's say. Then I stop this thing, and I stop computing this with presentation. So thank you.